Okay, thank you for the introduction. My name is Matveev, and I will give a talk here. So, first of all, I would like to thank the organizers for inviting me to the conference and giving me the opportunity to present our research here. I will give a talk about one of the most interesting things in quantum physics today, which is a Proton size puzzle. And maybe one approach to this problem based on frequency spectroscopy of transition one space and hydrogen. So just to start the talk, I will tell you the story about. Thanks. I just want to tell you the story that several years ago, when I was a PhD student in Moscow Institute of Physics and Technology, we all had to pass examination in philosophy. And in one of the seminars on philosophy, our teacher asked us generally what kind of research we do. And I answered hydrogen spectroscopy. And then he asked, so what is interesting in hydrogen? Because everything was done already many years ago, and it looks like there is nothing what you can extract from hydrogen. All fundamental laws already know. So that time I didn't know what to answer, but after some hours I just understood that you can say this about the whole physics at all, maybe except cosmology, because only in cosmology we don't know fundamental physics. Some time ago you can also tell something like this about the particle physics, but after Higgs boson discovery it's also become really boring there. The good question for motivation of all physicists in the world is where we can find a new physics, or traces of new physics. So, as experimentalist, I would answer that probably it's obvious that we should do something which nobody else did before. And that brings us to the two possible choices, which we can proceed. We can do some extreme physics, so try to go to parameters or conditions which nobody tried before. Like, for example, we can take two protons, accelerate it to energies which nobody tried before and collide together. But this extreme physics usually takes a lot of money, because you need to build another accelerator or another space mission, so it's billions and billions of euro. So, second opportunity, what we can do in small teams and small budget, is to try to develop the precise physics. That means that we don't try something really, really new, we just try to test the fundamental laws which we already know on higher and higher level of accuracy, just improving our techniques. And this doesn't need so much money. So, but we need to be very, very precise there. So as soon as we go to precision measurement, I will just, maybe everybody knows that the best thing which we can measure at all is a frequency. This is because it's very easy to measure frequency precisely. So what you need is just very good clock, and then you can measure the frequency of some radio frequency source just by counting the cycles during the known time gate. And just divide a number which you get to the time interval duration, and then you got the frequency. And this is very easy and needs really primitive electronics for it, and gives you really good accuracy. So, for example, 10 MHz source in 1 second, you can easily count with 10 to minus 7 accuracy. So, which is just a starting point, which is really good. Of course, the more is the frequency of your source which you want to measure, the better precision you can get. But, of course, everything is limited by the speed of electronics. But in optical domain, there is another technique which already granted with a Nobel Prize in 2005, which is called frequency comb. So the idea is very simple. So if you take radiation of femtosecond modular laser, which is just a series of pulses with constant time interval between them, and see what is the spectrum of this laser, you will see that it's an array of the very narrow modes with frequency of every mode equal to n times repetition rate of the laser plus some offset frequency. So a repetition rate is very easy to measure. You just count the cycles again with a radio frequency counter. And it's a bit more difficult to measure the offset frequency, but you can do it if you make the interference between the initial radiation of the laser and frequency doublet radiation of the laser. In this case, you can just extract the offset frequency from the big node signal, which we can observe. Of course, you need really broad spectrum for it. But then, after that, you can measure any frequency of any mode of the laser just because you know very precisely two frequencies, omega offset and repetition rate of the laser. So then if you need to measure frequency of some continuous wave laser, you just take this laser, make a bit node with a comb, and measure the difference between closest mode of the comb and the laser, again with counter. So instead of counting the optical cycles of the laser, you count 3 different radio frequency signals and then reconstruct what you should get there. So this technique is commercially available, and it generally opens a possibility to construct huge variety of different precise frequency measurements in different laboratories. So this is a typical scheme. So you just take the good optical good clock. So the best is cesium photonic clock, but you can also use atomic clock like hydrogen maser or radium clock. You can also reference the GPS if you want. Then you use femtosecond frequency comp to measure the frequency of your laser system. You just do it continuously, and then with the laser system you scan the frequency of some atomic resonance. Better to use some narrow resonance, but not necessary. And then with this scheme you can extract the frequency of atomic transitions very good precision. So for example, we got 1s2 frequency in hydrogen with 10 to minus 14 accuracy, and accuracy like 10 to minus 18 already achievable there. And second question, what is so interesting in particular in hydrogen? So the answer is very simple. So if you want to find the traces of new physics, you want to compare the theory with experiment, and you also require that theory also should be very precise there. And as you probably know, the Schrödinger equation can be solved analytically only for two-body systems like hydrogen. And for helium or lithium, it can be solved numerically with any required accuracy, but it's already a numerical calculation. And for heavier things, it's already start to be difficult. But of course, the simpler the system, the better to work with this. And for two-body systems, we can work only with atomic hydrogen generally, or hydrogen-like ions, and there also exist some exotic systems like positronium or muonic hydrogen, and so on. So if you practically try to calculate the frequency of transitions in hydrogen from the set of fundamental constants, so you will quickly find that the uncertainty of energy which you get is defined by uncertainty of two constants. So Riga constant and Proton charge radius. Of course, there are also constants like fine structure constant alpha or electron to proton mass ratio, but they know with higher accuracy, so they don't limit the calculation accuracy. So there are two constants in this game, Riga and Proton charge radius. But as experimentalists, we can also say that, okay, if I have this, I can just measure two different transitions in hydrogen, and then from two different transitions, I can reconstruct the two constants. It will be a nice measurement of two different fundamental constants. And actually, this situation is even easier because one transitions, namely 1s2s, we already measured. So this is the results which we got in 2010, also with Yanis Alnes, who is now here. And this number is very well known. So relative uncertainty here is 1.4 times 10 to the minus 14. So if you just measure one other transitions in hydrogen, not 1s2s, but 1s3s or anything else, you can extract the two constants. And that's very easy to do. So of course we can do it with the measurements which was done before in hydrogen. So this is different transitions in hydrogen. And generally you can also extract it without using 1s2s from lamp shift, 2s2p measurement. And here you can see the proton charge radius, the error bars for different transitions. So as you can see, statistically the results nicely agree with each other. This is why co-data committee, which published the recommended values of fundamental constants for everybody, they just used to average these numbers together and got this value. So there is also other ways to measure the proton charge radius. For example, you can use the accelerator experiments. So just take the beam of electrons and scatter them on proton target. So, and in this case, from the data you can also extract the proton charge radius. So here you can see how this points, they also generally agree with each other. They also agree with the hydrogen, which is here, atomic hydrogen. So this is why CoData also just average out the results which was obtained in this area and publish the CoData 2006 value. And then there was more measurement with electron scattering, and they published another value which is even has some smaller uncertainty. So looks like everything is fine, but in 2010 was published another paper. It was done by PSI collaboration. So they measured the proton charge radius using another method, which is called spectroscopy of muonic hydrogen. So the idea is very simple. They take a beam of muons from accelerator, they decelerate them in the system, and then put in a hydrogen target. So the muons are 273 times heavier than electrons. They just kick out electrons from the shell of hydrogen atom, and they form the special exotic system of proton and orbiting around that muon. So since muon is much heavier, again, it's very close. Its wave function in zero is 173 square times cube times higher than for electron hydrogen, and then sensitivity to proton charge radius and proton structure of this measurement is much higher than we can get in atomic hydrogen. So they can measure the proton charge radius with much better accuracy than everybody else can do, and they got the results which completely not coincide with everything else. So with last CoData, 7 sigma is discrepancy, and this is known now as the proton size puzzle. So since nobody succeeded yet to explain this effect, so we don't know why it happens. So it could be that we have a problem with theory. Of course, we cannot really just solve this problem immediately, but any information, new information about proton size will be valuable. And in our group, we are trying to make another measurement of proton size using another transition in hydrogen and new method. So what we want to do is that we want to measure the transition 1s, 3s in atomic hydrogen. So this is a structure, level structure, which you well know from the course of physics. So 1s, 2s transition is measured well, and then we can use 205 nanometer laser to excite atom to 3s state. So generally this measurement is done now with precision around 10 kilohertz, and to make some good addition to proton size puzzle, we need accuracy around 1 kilohertz. So like 5 kilohertz will differ us from muonic hydrogen point and CoData point. And of course we also want to use some novel method. And our method is based on two-photon spectroscopy. We just want to use comps instead of continuous wave. So just to quickly remind, what is it? So I will explain how works the spectroscopy with continuous wave. So you just take the normal Fourier cavity and create a standing optical wave between the mirrors here. So if moving atoms absorb two photons from the cavity to get excited, you can absorb two photons which are traveling exactly in opposite direction. In this case, you compensate exactly the Doppler shift, the first order Doppler shift in this case. So when you make this measurement, you should see the narrow peak of Doppler free excitation on broad pedestal of Doppler gradient excitation. So of course there is a residual second order Doppler shift, which is special relativity effect, and we cannot do anything with this, especially for hydrogen, because hydrogen you cannot cool down with laser means, laser technology. Just only thing which you can do is to cool it using the liquid helium cryostat. So it's not very good cooling, but it's the technique which is available today. So what we can do new is, instead of the continuous wave, as shown here, we want to use the frequency comb, so mode-locked laser. So we need to take the Fabry cavity and put there 2 pulses of light, so they should collide in some volume in space, so which we call pulse collision volume. So in this pulse collision volume, the atom can absorb 2 photons which are traveling in different directions and get excited. So what is important to say here is that first of all, the Doppler shift is not cancelled completely because the energy of 2 photons shouldn't be equal, because the spectrum is quite broad, and this difference can give additional broadening. So quite recently we found that there is also a shift corresponding with a possible chip of the laser. It was actually dominating systematic shift in our measurement, which we want to process and publish now. And another thing is that since we have a repetition rate, then usually we fix the repetition rate of the laser and scan the offset frequency of the laser, and this is resonance condition. So the resonance repeats itself after every repetition rate of the half repetition rate of the frequency comb. So just to make this measurement, what we do is in vacuum chamber we create this cavity with the 205 mm radiation, and in the center of the cavity we have pulse collision volume, and near this we put the copper nozzle which creates the beam of atomic hydrogen. So we just take the hydrogen from the bottle, then it passed through palladium purifier, and then we use microwave discharge to split molecules to atoms. Then Teflon tubes guide the atomic hydrogen all the way to the nozzle, then it just flies in the vacuum. And close to the pulse collision volume, where the concentration of atoms is high enough, we just put the pulse collision volume. So what is not also shown here, that there is not only one detector of excited atoms, so where we can consider excitation, but we have also detected the Doppler broadened signal in other place. It helps us to show, to track all noise which we have, like fluctuations of laser power or atomic flow and so on. So just to detect the excited atoms, we use the decay from 3s state to 2p state. It emits the red light, 606 nanometers, with volume alpha photons. So since in this kind of method, measurement with the frequency combs, we have a good advance in comparison with continuous wave laser. So this Doppler broadened background is emitted everywhere, and Doppler free signals emit only in pulse collision volume. So if we can localize our detection scheme only to pulse collision volume, we can generally suppress the background, which is Doppler broadened one. So this is why we construct our detector this way. So we use aspheric lenses which collect the light of the fiber, then multimode fibers come out of the vacuum chamber, and the light is passed through interface filter. Then we count the pulses with the photons with photon multiplier tube. So it's a scheme, and it generally works. So this is how the detector assembly looks like. So there is just very small aluminum part. Here are also the aspherical lenses which collect the lights to the multimode fibers attached here and here. Then everything is outside the vacuum chamber. Also important thing is that for this kind of spectroscopy, what we also would like to have is that we want to control the polarization of the pulses. Ideally, we want to have different polarization of 2 pulses, and they should be circular, so single plus and single minus, for example. So of course, if you just couple the laser light into the cavity, you cannot do it. So we had to use additional interferometer in the system. So just the delay stage. So light which is coming from the laser system just split it into parts. So half of the radiation just comes to the cavity and then just forms first pulse. And second is delayed in this arm exactly to half propagation period, and then also comes to the cavity. So they have 2 different polarizations, and with the quarter plate which is shown here, we can also make it circular and with different directions. So, and in addition, this scheme helps us to make kind of dirty trick. So we can efficiently double the repetition rate of our laser. We want to have it as much as high as possible, and this gives us factor of 2. It's not, of course, the real doubling of repetition rate on spectrum of the laser, but we can use the fact that the excitation of the atomic pulses is proportional not to the electric field, it's proportional to a product of electric field of 2 pulses, and the product, in product of this electric field, so the pulses on spectrum of the products, you have additional second peak, so you just efficiently double the repetition rate of the laser. So this is the sketch of our laser system, generally used for this measurement. So our working course is a mode-locked titanium sapphire laser, so which works not in femtosecond but picosecond regime. We like to use the picoseconds because of this effect of residual Doppler broadening. So you want to have relatively narrow spectrum of the laser, because if you have broad spectrum, you have residual Doppler broadening. Then the radiation of picosecond laser just frequency doubled twice into different cavities, and from 820 we got 205 nanometers, which is going to the laser system. We go to the vacuum system already and the late stage, and so on. Just to control the frequency of the mode-locked titanium sapphire laser, we phase lock one of the mode to the ultra-stable diode laser. So this is well-developed technique to construct ultra-stable laser systems. So we just take the laser and then actively lock it through boundary hole lock to the very stable, specially designed, thermally stabilized cavity. And with this you can really get 1 Hz line of the laser. So, and this is used as a reference for us. It's flywheel, so we lock the laser to it, and then we can also add the additional shift to change the frequency of the titanium sapphire laser. So the radiation of continuous wave, that laser is just tracked with the help of another femtosecond frequency comp versus hydrogen maser. And the frequency of hydrogen maser I continuously track using the GPS receiver. So using GPS receiver I can get accuracy of estimation of frequency of the hydrogen maser within 4 times 10 to minus 15. So I wouldn't trust more than this level. And this is generally limiting our accuracy of estimation of frequency. But of course the main troubles are coming here inside of the atomic system. So since 1s/3s transition is really broad, it's difficult to measure it very precisely. So this is the example of our line. It's just a screenshot from the program which I use for processing of the data. So you can see the red and green data from 2 channels. One of them is used to, this is Doppler free signal from pulse collision volume, and this is the reference from Doppler broadening background. If you just divide one by other, you see a nice line. You can very well fit it, and you can also see the record of the continuous wave bit node, continuous wave laser bit node during the time, just to start the frequency. So it's just this one scan is done during several minutes, and it gets already to 70 kilohertz uncertainty with one single scan. So if you try to measure for 1 day, approximately, this is the result which you can see here. We can easily get to 10 kilohertz during 1 day measurement. So we are in good enough shape to at least to get better measurement than it was done before in terms of statistics. If we can get rid of systematic effects, so it's possible to do it better than before. And just to conclude, I will also list the systematic shifts which you have in experiment, and this is really a big headache for us, because many of them are difficult to get rid of. Unfortunately, I didn't type here numbers. I should do it. So the biggest effect, probably, for us is the second order Doppler shift, which is correspondent to the fact that in velocity and frame of the moving atom, time is going with different velocity. It's just special relativity effect. So to get it under control, we need to know our velocity distribution of the atoms. We don't know it very precisely, so totally this effect for us is like 75 kilohertz, and we can estimate the accuracy like 10 kilohertz only. So we got also the big pressure shift because atoms collide with each other in the atomic beam, and this effect will also level of 20 kilohertz. We can estimate the level of 10 kilohertz level. So probably the biggest effect, which really kills the last measurement, we should try to do in November and December. So we will still publish the data, but the uncertainty will be on the level of 30 kilohertz. And the biggest problem was concerned with the Doppler shift, which is concerned with the chirp of the laser. So the problem is that the tensor fire lasers usually have a chirp, and for picosecond laser it's very difficult to compensate it. And we didn't get idea now how to do it, and we're still working on it. But this actually limits our accuracy on level of 30 kilohertz level. So, and there are also a huge variety of other effects like DC start shift, AC start shift, electromagnetic field shift from them. Also very interesting effects concerned with the line poolings by 3D lines, which we can also observe. And also shift from quantum interference of decays from 3S state and 3D state. So, but this shift's already under control. We really have to find the problem with the biggest effect for us. And right now we still want to publish some first data on the 30 kilohertz accuracy. It will not be the best measurement of 1s3s, it will not be also solve the proton charge radius, but it's kind of step forward towards the good measurement of 1s3s transition. I think I have already time, so maybe I would like to thank everybody for your attention and just I will have to answer questions.